Right, well, I've just made this new download available from the website, and it is UFO-CFD Octree 2018. So I thought I'd have a quick run through of what to do with it once you've downloaded it. So first of all, we can extract it. So the files we've got in here, the important ones, are the geometry, this Ferrari geometry STL file, the octree solver, which is an executable file, and the octree text input file. They're the three important files: geometry, the solver, and the text file. If we load PowerView, read in the geometry, check that it's all there. It's okay. If you have a look at the text file, so this is a bit different to the original UFO-CFD, which had some kind of GUI, but for this octree version, I've just gone for a straightforward text file which you write to directly. So you put the name of your STL file at the top, and then you fill in these variables below. So the STL file needs to be an ASCII one. You put the number of refinement levels, it's set as 9. The level of the background mesh that you want, 4. And the number of blanket layers that you want has been set to 3. And then there's some variables here. Because it's dynamically allocated, you can increase or decrease these as you wish, but the important thing is that they're large enough for the geometry or the mesh that you're creating. So I've got the triangle limit of the STL file set to 200,000. The number of octree cells is set to 4 million. And the number of octree points is set to 9 million. Next, you have to position the root cell, or the largest octree cell, relative to your geometry. So we set the size of the root cell as 12 meters, and then position it at 060. So that positions the root cell relative to the geometry. So basically, the geometry has to be within this large box. I can set the solver on or off. So I might just want to look at the mesh, in which case I can switch that off. I can select ASCII or binary output or no output. So I've set this to binary. I've got the low velocity modification on because it's a low speed case. The number of iterations for the solver is set to 10,000. The save frequency is set to 1,000. So it'll run for 10,000 iterations, saving every 1,000. Then I've got a few basic solver parameters here: the CFL number, the minimum smoothing. So this is the solver averaging. The max smoothing 0.5, wiggle cut off one that's related to the size of the pressure perturbations in the solution. The wall function is set to 1, which basically means that the near wall velocity is not being reduced at the moment. If I decrease this, then it will reduce the near wall velocity. Got some fluid properties here, and then last of all, I've got the free stream properties. So U velocity, V, W, density, temperature, and pressure. So we can try run this and see what happens. So I'm running this from the command line at the moment, so I can see what's going on. So these are the files that we've got. These executables here, one is just for timing the runtime, and the other one is just for redirecting the output to file. They're used if we run the batch file. I'm octree the conf.dat. I mean, you can just run the octree file directly, but I run it in batch mode so we can see what it's doing. I don't know why it started running the solver. I run there, I think I forgot to save it. So it's read the input file, it's read the geometry, it's generating the mesh, and then it's done that so quickly, and it's just written out the file. So that has taken about 10 seconds, and it's generated 402,000 live cells and 856 leaf cells in total. And it's telling us there's 909,000 points. So we can read that in. It's a binary file, so it reads in pretty quick. As you can see, that's the largest octree cell that has to encompass the geometry. So if we take a cut plane through that, you can see the mesh that's been generated around this car. Get rid of the geometry. See the overall mesh. And we're looking at the levels here. So if we put a legend on, we've got level 4 in dark blue. That's the background mesh that we specified. So the root cell is level 0. And then every refinement of that is one level above. So this is level 4 as the background, level 5, level 6, level 7, 8 and 9. So we've got a level 9 mesh around the car geometry. We can look at the distance field. The distance field isn't really used by the solver, but it is useful for displaying the surface of the geometry, because apart from the STL geometry, we don't have any other way of visualizing the surface of the geometry in the flow solution. So that's why we need to save the distance field. We've got distance field, level, and LCD is live, cut, and dead. So that shows us explicitly cell by cell whether it's a dead region, a live region, or a cut cell. And you can see that it's all blue inside the car, so there's no leakage between the outside and the inside regions. So if we do cell data to point data on the overall mesh, then we can create a contour and select the distance field. And if we set the distance field to 0, that shows us the surface of the geometry in the flow solution. We haven't got a flow solution yet because it's not done any iterations. We're just looking at the mesh. And we can see that it's not captured the geometry very well around the wheels because the mesh is not fine enough in that area. But if we overlay the geometry, you can see that it's pretty much coincident with the distance field.